Hi everyone. In this lecture we're going to discuss selected material from Chapter 3 of your text titled Perception. Perception is the experience resulting from the stimulation of your senses. The basic concepts we're going to cover when we're talking about perception are the fact that perceptions can change based on added information that we accumulate over time, and also perceptions occur in conjunction with other actions as well. There are two main approaches to understanding perceptions, and the first of which is direct perception theories, which includes bottom-up processing. And this idea is one in which we basically piece together perception from stimuli in our environment, and parts are identified in the environment and put together, and then recognition occurs of things that are in our environment. So basically, we're building things in our environment from the bottom up, piece by piece. On the other hand, conversely, constructive perception theories include top-down processing, which is kind of the exact opposite of bottom-up. And this type of idea, people actively construct perceptions using information based off the things that they expect to see. So kind of what we're perceiving is based off of more what our expectation is of what we're going to see. That's the best way to think about top-down processing. With bottom-up processing, it could be that we have some sort of perception starting with what's coming into our senses. So incoming raw data, things such as smell or things that we might see, very raw data coming into our senses may start our perception of what's going on in our environment. And conversely, top-down processing, the perception may start with the brain itself. So we may again start with a person's prior knowledge, experience, or what their expectation is of a given event or environment. This might heavily influence what their perception actually is. Here we'll take a look at how this might work for bottom-up processing. So if we take a look at this, this would be how Mary is represented in Gil's nervous system. So we have an image on Gil's retina by electrical signals in the optic nerve. And then from here, we have electrical signals in the brain. And now we're building this perception of Mary here based off of a piece-by-piece type of perception. So this again would be more bottom-up processing. And here essentially would be the opposite. So this is kind of where we might use top-down processing. So we have something like a blob here in A. And of course we have no idea what this blob is because it's not in any kind of context. Whereas if we look here, for example, at this particular blob, given, like obviously we can't see what this is, but given the context of what the whole picture is, it's obviously a person kind of squatting down. So we would assume that this blob here is a foot. So we're kind of taking the whole context of the picture here and from that breaking it down to the point where we can figure out what this is here. And this again would be, of course, a foot. Now, if we look at D, again, the same thing. Just looking at these blobs individually, it would be really difficult, if not impossible, to tell what they are. But placed into the context of this picture, we can see that this is a big building here, and this is a street. So this right here then would be a car, and this would be a person. So again, we're doing that based off of the whole context of the environment, and from that we're extracting out information about what these blobs are. And again, this is based off of our, of course, prior experience and also our expectation of what we would think to see once we actually acknowledge that this is a street. We would think that this would be a car. And over here on the sidewalk, we would think that this would be a person. So it's just a quick example of how the two different types of perceptions may operate. We can also see an example of top-down processing when we're trying to understand sentences, particularly in a foreign language. So if you've ever noticed when you're hearing a foreign language, your ability to pick out or understand certain words is really highly based off of context. And again, this is demonstrating top-down processing. So for example, if you've had some experience with Spanish, but you're certainly not fluent, if you know you're listening to a baseball game, you might be more able to pick out certain words, such as players' names or just, the word ball or pitch, things like that you could pick out. Whereas if you didn't have that context to place the conversation in, you probably wouldn't be able to do nearly as well. And our ability to separate words in a sentence is something we call speech segmentation. So this is our ability to tell when one word ends and the next begins in a sentence. Now, we don't notice it because we're fluent English speakers, but as I'm speaking to you, you know where one word ends and the next begins. It's very easy for you to tell that. But for someone else who's not a native English speaker, it sounds like all of my words are running together. And that is exactly what it sounds like for us as native English speakers listening to other languages. So, again, this ability to separate words from one another in a sentence is speech segmentation. And again, when we're listening to a foreign language, we do better at segmenting words out from different sentences when we have some sort of context to put the conversation into. And again, this is more of a demonstration of top-down processing. Now, if we take a look at how we might perceive pain, we do have an idea of a direct pathway model. And this model is an earlier model that emphasizes that we have certain receptors that would send pain messages directly to our brain. And this is more of a bottom-up processing model. But more recently, we do have a top-down idea. One in which we found that expectations of pain, how much attention we pay to pain, and also how much distraction is involved can affect how we actually experience pain in more of a top-down manner. And we can think about the placebo effect in this way. So most of y'all are very familiar with the placebo. Basically, this is a sugar pill in substitution for another drug. And what we found, of course, is if you tell someone they're getting a certain drug and these are the side effects that could occur from that drug, and you give them a sugar pill, a lot of them will report experiencing these side effects or just saying, oh, this pill's working, I feel better. We just see effects like this basically just because they're told to expect certain things, and that's what they report that they feel after they take the drug, when really, of course, we know they've just taken a sugar pill. So this is just kind of giving us some evidence that suggests that our expectations of a certain event could affect highly how we perceive the event. And again, this is more of a top-down idea. Now, if we move on to Helmholtz theory of unconscious inference, this again is more of a top-down theory. He thought that some of our perceptions are the result of unconscious assumptions we make about the environment. And this would, of course, be using our knowledge to inform our perceptions. So prior acquired knowledge from prior experiences would kind of be swaying our current perceptions based off of his idea. And he suggested that we infer much of what we actually know about the world. So basically, we're just kind of taking guesses. And this theory is largely based off the likelihood principle. So basically, we perceive the world in the way that is most likely corresponding to our past experiences. So basically, based off of prior experiences, that's how we make predictions about what's going to happen right now, and that's how we're likely to perceive an event, even if it's not entirely accurate. And this would be kind of a very easy example of Helmholtz theory. So if we see something like what's in figure A here, we would most likely probably assume that what is actually happening here is that we have these two items, and just the blue is laying directly on top of the red item. So the blue rectangle is laying on top of the red rectangle. That's what we would assume probably when we see this, because the vast majority of the time when we see something like this, the blue rectangle would just be occluding a large part of the red rectangle. But it is also possible that we could have this scenario here, what's demonstrated in C, and that is that there's a big chunk here out of the red rectangle, so it's not actually a rectangle. So these two fit flush in together. So again, we would assume that it's probably this configuration, but again, we have to acknowledge it could be this one. But the reason why we assume that it's this one is the vast majority of the time when we see something like this, it is something like this. So this is just an example of how his theory would work. Basically, our prior experience suggests that this should be what's going on, and so we probably assume that just based off our prior experience. Now, if we focus on how we organize the things we perceive from our environment, the old view, which would be more of a structuralism view, just suggests that we basically add up all of these sensations that we're receiving from the environment, and that basically constitutes our perception. So we have that example here on the right side with this dot drawing. So basically, their idea was that we would add up all of these different dots to create our perception of this lady's face. But a newer view, which I'm sure some of you all have heard of, Gestalt psychology. This is where these guys are really playing a large role. This is a newer view, again, of perceptual organization. And the idea here is that our mind groups patterns according to laws of perceptual organization. That's the suggestion. And we'll take a look at each of the laws in Gestalt psychology on the next slides. And the first law that we're going to take a look at is the law of good continuation. And this just suggests that lines tend to be seen as following the smoothest path. So here in figure A, we just have a lot of rope kind of wrapped up here and just kind of thrown on the ground. Now, if we take a look at picture B, this is just an example of how we can kind of pick out a strand of the rope and perceive it as being a single strand and kind of follow it around how it's wrapped within the rest of the rope. And this law of good continuation, according to Gestalt psychology, is what helps us to perceive this as being a single strand and helps us actually follow it along. Rather than just seeing everything as just this big wad of rope, we're actually able to pick out individual strands and trace them through. The next law is the law of pragnance, or simplicity or good figure. And what this law suggests is that every stimulus pattern is seen so the resulting structure is as simple as possible. So this is why if we take something like the Olympic symbol, we see the Olympic symbol as being this. So we see it as being a bunch of circles kind of overlapping with one another, rather than seeing it like this. So if we saw it like this is of course 9 shapes, right? And this is only 5. And the simplest way to see this would be the 5 shapes overlapping rather than seeing 9 individual shapes. And again, this is just the idea that we see things as simply as possible. So the structure being as simple as possible. Next we have the law of similarity. And this law is just suggesting that similar things appear to be grouped together. Now, if we take a look at A, of course here we tend to perceive this more as horizontal rows or vertical columns or both because they're all the same. But here, if we take a look at B, we definitely perceive these more as being vertical columns because we're grouping red items with red items and blue items with blue items. We're grouping liked things and we're perceiving them as being grouped together based off their similarity. So we naturally would see B more as being vertical columns rather than horizontal rows, just because we're grouping the like items and perceiving them as being grouped together. Gestalt laws often provide accurate information about properties of the environment, and they do somewhat reflect our experience. So our previous experience we've had with these types of objects and things like that in our environment, and how often we've had to use these properties of organization according to the Gestalt laws. However, the experience is important, of course, again, but it doesn't overcome perceptual principles. The suggestion with Gestalt psychology is that these Gestalt laws are intrinsic or are naturally occurring within us. So we have a natural tendency to use these perceptual principles that Gestalt psychology lays out. Now, if we move on to physical regularities, we take a look at the oblique effect. This is just the effect that we see when people can perceive verticals and horizontals more easily than other orientations. And the suggestion, I think, here is that we see a lot more verticals and horizontals in our natural environment, so we have an easier time perceiving those than we do diagonal orientations, for example. And also the light from above assumption. Light, of course, usually comes from above, and is usually the case in the environment, in our environment. So whether we're outside or inside, light is usually coming from above. And based off of this, we can perceive shadows, kind of using specific information about depth and distance based off of the light above assumption. Now here we take a look at examples of both the oblique effect and the light from above effect. So if we take a look at figure 3.22, this is just showing natural pictures, looking at trees, of course, and then rock formations. And what we see the two have in common is a lot of verticals. We see a lot more verticals than horizontals in our natural environment. And even when we're building skyscrapers and things like that, we're building them very much as verticals. We're not building them as diagonals. So these things are just a lot more common in our environment. Now, if we look at figure 3.23, this is looking again at the light from above effect. So we're looking at picture A and picture B, and these are the exact same picture of the exact same wall, but they look quite different. In picture A, it looks like this textured surface is protruding, whereas in B, it looks like it's recessed. Now, this is happening based off of the light from above and where it's hitting the wall. So in A, if we look at this, the light would be hitting the top part of this textured area. And if that is where the light's hitting, then it's going to make these areas protrude like this. Whereas if the light from above is hitting the indented section here, so the bottom of this indentation, then it's going to look like the textured section is actually recessed. So again, this is all about where the light's hitting an object and the angle of which it's hitting it, which is really changing our perception of the wall, which again is the same exact wall. So one idea of how we make inference about perceptions that we are going to have, basically inferring what we're going to perceive before we actually perceive it, was suggested by Thomas Bayes, and it's called the Bayesian inference. And he suggested that our estimation of the probability of a given outcome is influenced by two factors. The first of which would be the prior probability, so our initial belief about the probability of an outcome, and also the likelihood of a given outcome. And basically, we would kind of factor these two things in together and come out with our idea or inference about a certain event, or just basically our perception of something. And here we take a look at an example of the Bayesian inference. So if we take a look at Mary's prior belief, if we look at probability as a function of different causes for a cough, in her prior belief, she thought there was a high probability of a cold associated with a cough, a fairly lower probability associated with lung disease, and then a high probability associated with heartburn. Now, if we look at her prior belief against the likelihood of one of these illnesses causing a cough, a cold would still be very high up. A lung disease now would be very high up, but then heartburn would be quite low. So if we factor both of these things together, so her prior belief along with the likelihood of these different things causing a cough, we get the conclusion, which would be that the cough would most likely be the cold would be most likely what's causing the cough in this case. So again, we're kind of factoring these two things together, and what we get out of the adding of the two together is kind of what we use as our inference or our conclusion about an event. So now if we look at neurons in the environment, some neurons just best respond to things that occur regularly in our environment, and I've kind of talked about that a bit in some previous slides. But basically, neurons become tuned to respond best to things that we commonly experience, things like horizontals and verticals, for example. So basically, we do have some plasticity, but it's kind of experience dependent. So what we're actually experiencing in the environment is kind of determining how plastic essentially, or flexible we are. Now, this was an experiment that's listed in your text using these little figurines called greebles, and they're all a bit different, but of course they're objects that we're not familiar with. And initially before training, if we're looking at response, so neuronal response, there's a lot more response initially, so before training. There's a lot more response to faces than the actual greebles. But after training, we find that response to greebles is almost up there with faces. So again, we see more responses just as a function of experience. So again, we are plastic, but we need to have that experience before we can actually start to respond to different things. Now, something else that facilitates our perception is just movement. So movement helps us perceive things in our environment a lot more accurately than if we're seeing still shots or static images. So if we see, for example, a horse standing at a distance, it might be difficult to tell that it's actually a horse until we see it walking. And once we see it walking, seeing the way it moves, it becomes a lot more apparent that it actually is a horse. Also, if we were to walk around that same horse and see it from different angles, it could also help us, kind of get an accurate perception that it actually is a horse. So if we, take a look at this cardboard cutout here, from one particular angle, maybe even this one, of course, the head is kind of telling. But as you can see, like if you were to walk around this cutout and see it from all angles, it's very apparent that it's a horse. But seeing it from, any one still angle, it might be kind of hard to tell exactly what it is and exactly its full shape. So again, it's just more helpful to get more views of the object and if possible to actually see the object move. It's a lot more telling and helps us actually perceive more accurately what the object is. Now, the last thing we're going to take a look at is the perception of basically perception and action. So basically, we're looking at a what and a where. So what an object is, for example, and where it's located. So we have our what stream, which is basically helping us to identify an object. We also have a where stream, which is helping us to identify the object's location. Now, if we take a look at a diagram of our brain, the what stream we'll take a look at first down here. So this is also known as the ventral stream. So again, this is object processing. So this is telling us about size, shape, texture, and color, for example. So basically telling us these type of details about an object and helping us to identify it. So again, this is all starting here in the occipital lobe. So this is where we're getting visual information, right? And then from here, this travels down through the temporal lobe and on toward the frontal lobe. So again, this right here, this red path here, is our what or ventral stream. Now also for our where stream or dorsal stream, this again is spatial processing. So this is telling us where in our environment an object is located. So this is of course again telling us location, but also spatial relations. So its relationship in space to another object, but also its movement. So how is it moving? Things like that. And again, we're getting this information again from the occipital lobe. That's where it's generating, right? Visual information. But then it's traveling the opposite direction up toward the parietal lobe here and then toward the frontal lobe. So we have two different distinct pathways here for what and where. Now, finally, in the last slide here, we can take a look at the effects of damage to particular areas of the brain and its effect on being able to identify what objects are versus where objects are. Now, if we take a look first here, if we have this area removed here, this is the temporal lobe. So this is basically for object discrimination. This person, if they have this this area here removed, this is going to really make it difficult for them to discriminate between these two objects because this, remember, this is the part where we have the what stream traveling through here. So this would be our occipital lobe here. This information would be traveling through the temporal lobe onto the frontal lobe. And if this section of the brain is removed, this person's going to have a very difficult time picking between these two objects and discriminating against them. Whereas if we look at B, this person has the parietal area removed. So the parietal lobe is removed. Now again, this is going to affect where. So if we have our information coming in, starting, occipital lobe, going up through the where stream, through the parietal lobe, onto the frontal lobe, if the parietal lobe's not there, this person is going to have a very difficult time figuring out where objects are in relation to other objects. So this person is going to have a lot of issues with landmark discrimination, for example. So if this person were told to pick the food well closer to the cylinder, well, we know that would be this one. But again, with this whole area removed, this person would have a very difficult time, if not just be completely unable to perform this task. So I hope this lecture is kind of giving you guys a better idea of how we might perceive things that are going on into our environment, the different ideas of bottom-up versus top-down processing, and the what-where pathways and things like that. So again, make sure to take a look at this chapter carefully in your text, and I'll get back with you when we go through chapter 4. Have a great week, guys.